Hi, I am Sanjay Patel. We are going to study the topic successive differentiation in our calculus course. So let us begin with some prerequisites. All of you have studied what is the meaning of derivative and how to compute derivative of a given function of one variable in high school mathematics. So just I am recalling some notations for this derivative. So suppose if we have a function y is equal to f of x, okay, suppose f y is equal to f of x be a given function which is differentiable, then its derivative we can write in many different ways. The derivative symbol, the basic symbol, as all of you know, is dy by dx. This is the first order derivative of y with respect to x. Okay, we can also write it as say f dash of x, or we can write this as f1 of x. Okay, another way of writing is say y dash of x, or we can write it as y1 or simply y1 of x. Okay, and one can also use the differential operator capital D. That D means dy by dx, and the first derivative, so I will write d1 operating on y. Some people also write like this, d raised to 1 y. So these are different notations for the first order derivative. We can go further and write the second order derivative also, like d2y by dx square. This is the notation for the second order derivative. We can write f double dash of x or f2 of x. We can write y double dash or y2 or d2y, or like this d square of y. Another one more derivative symbol, the third order derivative d3y by dx cube, that is f triple dash x. This we can also write as f3 of x or y triple dash or y3 or d3y or d cube y. Okay, so these are the different notations, but some symbols or notations are not convenient when you go further for the higher derivatives. Like this notation, the dash symbol is not very convenient. So as far as the lower order derivatives are concerned, say first, second, or third, we may use these symbols. Otherwise, the other notations are more, say, convenient and preferable. So let me write down finally the general form. I can say in general, the nth derivative or the nth order derivative dny by dx raised to n, we can also write it as fn x. We cannot put n times dash, just we'll write this notation fn x. We can write yn, okay, or we can write say dn y or d raised to ny. These are the notations for nth order derivative where n is any natural number. Okay, now in this chapter we want to prove some results regarding the nth order derivative. Actually, we are differentiating a given function again and again, so it is called successive derivative. For example, consider a simple function. Say, let us take y is equal to e raised to 3x. Now, if I differentiate this function, with respect to x, then I will get its first derivative. I will use the symbol y1, or you can write dy by dx also. So y1 is 3 times e raised to 3x. All of you know what is the derivative of e raised to something, that is e raised to something, and the derivative of this power is 3x, that is 3 into 1. Now going further, for the second derivative, the next successive derivative, that is y2, that is derivative of y1 with respect to x again. So these three, as it is as a multiplication, it is in multiplication, and e raised to 3x derivative is 3 times e raised to 3x. So the final answer here is 3 square into e raised to 3x. Now you will understand and say the third derivative will be immediately 3 cube into e raised to 3x. So what is the 10th derivative? If you continue like this, y10 will be 3 raised to 10 e raised to 3x. So in general, we may conclude that the nth derivative or nth order derivative of the given function y is equal to e raised to 3x is 3 raised to n into e raised to 3x. Okay, and we may assume that this is true for every n belongs to n. So this is our statement. So if y is equal to e raised to 3x, then we have this conclusion that yn is equal to 3 raised to n into e raised to 3x by our observation. So what we are going to do is we will prove this using mathematical arguments. If y is equal to e raised to 3x, then we prove that the nth derivative yn is equal to 3 raised to n into e raised to 3x, and we want to prove this for every n belongs to n. So one can write such a statement from this observation. And as you know, if a statement in mathematics which is to be proved, which is dependent on n, where n is a natural number, and if you want to prove it is true for every n belongs to n, then we use always the principle of mathematical induction. So we shall use PMI, that is principle of mathematical induction. We are going to use the first principle, mathematical induction, and remember all our results or all the formulas what we are going to derive for some standard functions in this successive derivative topic using the principle of mathematical induction only. So let us recall quickly what is PMI, the first principle of mathematical induction. That is second also, but we don't need that at this time. So let me explain what is principle of mathematical induction. Suppose we have some statement, let P of n is some statement which we want to prove for every n belongs to n, and this statement P of n means it depends on the variable n. So n is involved in this statement, something like this statement yn, which we are required to prove for every n belongs to n. So we call this statement as P of n, where n belongs to n. Okay, then the first step number 1 is verify that P1 is true. P of 1 is true. That means prove that the statement P of n is true for n is equal to 1. So what we should do in this case, suppose if I consider this as my P of n, I should prove y1 is equal to 3 raised to 1 into e raised to 3x, which is simple. We'll discuss it later on. First, let me write down the steps for this PMI. The first step is verify the result which is to be proved for n equal to 1. Then step number 2 is assume that result is true for n is equal to k, means assume that pk is true, where k is some natural number. It can be any natural number, okay, but we fix it. So we assume that this Pn is true for some n is equal to k, and then using the truthness of pk, we prove that pk implies pk plus 1 is true. Rather, we prove that pk plus 1 is true using the fact that p of k is true, or using our assumption that pk is true. And then because of this, we can conclude that P of n is true for every n belongs to n. So in the PMI process, first verify the result is true for n equal to 1. Then assume that the given statement is true for n equal to k, where k belongs to n. And then prove that P of k plus 1 is true. That means the result P of n is true for n is equal to k plus 1. Hence, what we are doing is Pk implies Pk plus 1 is true, and therefore we can conclude that P of n is true for every n belongs to n. So these three steps are to be performed in all the results what we are going to prove. Okay, that is one important thing which is prerequisites in this topic. Okay, and next I want to also explain some basic thing about factorial which will be required at some places. All of you know what is a factorial. So if n is a natural number, if n belongs to n is a natural number, then we know that we define n factorial is equal to 1 into 2 into 3 up to n. So product of the first n natural numbers. There is another notation also for factorial n. We can also use the symbol ln. This is also called factorial. So you can use any of these two symbols for factorial. Okay, so that is one thing. And also we define that 0 factorial is equal to 1. So remember, this factorial we define only for natural numbers and for the number 0. Factorial is not defined for negative integers. Okay, now next thing we require is suppose you have, let us write some few values. Say 1 factorial is equal to 1, 2 factorial is equal to 2, 3 factorial means 1 into 2 into 3, that is 6, 5 factorial is 1, 2, 3, 4, 5. So it is 120. Okay, like that. And suppose we have something like this. If I want to simplify, say n factorial upon n. N factorial means 1, 2, 3 up to n, and it is divided by n. The previous number here is n minus 1. This n will be cancelled, and we can write this as a product of first n natural numbers. It is nothing but 1 upon n minus 1 factorial. It can be other way also. It can have n upon n factorial. Like suppose I have some simplification at some place like 8 upon 8 factorial. Okay, so that I can write directly this is as 1 upon 7 factorial. Or if I have 100, okay, 100 factorial upon say 99, I can, if I have 100 factorial upon 100, I can write it as 99 factorial because that 100 will be cancelled. So this is very useful. And one more thing is useful is the combination symbol. You know what is NCR? NCR means n factorial upon r factorial into n minus r factorial, where n is a natural number, okay, and r is also an integer between 0 to n, okay. So r is a non-negative integer between 0 to n. So for a fixed value of n, suppose if your n is equal to 4, then we can take possible value of r as 0, 1, 2, 3, and 4. And hence we have these 4 possible values of this NCR: 4C0, 4C1, 4C2, 4C3, and 4C4. All this you know very well. Just I am reminding you. This NCR can also be denoted by another notation, and that is, it is NCR. We can write like this also. Both are the symbols for this number of combinations of selecting R objects out of given N objects. You know what is the meaning of combination? Okay. Some useful things about this NCR symbol, which are useful formulas, and that I want to tell you. The first thing you remember is this NC0 is always 1, and NCN is also 1 for every n belongs to n. So 3C0 or 3C3 is 1 for any natural number. Second thing is say NCR is equal to NCn minus R. Because R is always less than or equal to n, I can write like this. And the third thing is say NCR plus n minus 1CR is equal to n plus 1 CR. It is something like this. Suppose I have 3C1 and 3C2. Sorry, let me write this way. This is a mistake. NCR plus NCR minus 1. This is the correct formula. NCR plus NCR minus 1 is n plus 1 CR. Okay. How to say remember this? When this n value is fixed and there is only one difference between the value of R, then we add 1 to the value of n, means we write n plus 1, and we take the maximum of R and R minus 1, that is R. So for example, if I want to add 3C1 and 3C2, here n value is 3, it is fixed in both the combinations, and here value of R is differed by 1. So we write 3 plus 1, that is 4 here in place of n, and the maximum value of R, that is 4C2. So this is also a very useful result when you prove some result, some theorem. Okay, so these are the prerequisites, and in the next lecture I'm going to explain how to derive all these type of formulas for successive derivatives. So we are going to start proving nth derivative formulae for some standard functions. Okay, till then, goodbye. Thank you.